So having learned about the Unruh-Davy detector and how it shapes up the transitions across the atom when it is talking to the background of scalar field, let us say, we landed upon an equation of transition across the atomic lines, which is probability of going from ground state to excited state. That we obtained is some integral transform of the 2-point function of the background field. So recall when we did this under first order perturbation theory, we obtained as the transition amplitude as a single derivative of the integration dt e to the power minus I delta et and phi of t squeezed between the initial states and the projected final state. Now, once we summed over all the possible Fock basis elements of the final state of the field, we ended up getting the transition probability of atom going from ground state to excited state, which is as a Fourier kind of transform of the 2-point function of the field. Now, this expression we had obtained for ideal or a demonstration case where the monopole operator of an atom was talking to the field through monopole coupling of the term m phi. That was the interaction Hamiltonian. Now, this exercise what we have performed is just a toy model towards a more realistic setups where indeed realistic operators from atomic side do talk to background fields in this manner. A case in point could be the electromagnetic interactions of fields with atom. For instance, typical atoms would have some dipole moment, which would be a vector operator property of an atom, which will talk to the background electromagnetic field through an interaction Hamiltonian of the kind d dot E, where the dipole operator vector d will talk to the electric field vector operator in quantum field theoretic language as d dot E term. And mod square of that under first order perturbation theory would give you very similar looking equations of probability of transitions as is depicted here. Here you could see the 2-point function of the electric field EIT EJT primed is appearing as a replacement of the 2-point function of the scalars which we had just obtained. Now see, there is a label I appearing across the 2-point functions I and j, and similarly in the dipole operators di and dj are appearing. This is because of their vector nature. In the monopole coupling term, the interaction Hamiltonian was m phi. In the dipole coupling, the interaction Hamiltonian will have term like d dot e, that is di ei sum over I. And when I do a mod square, I will have a twice of these terms. So I would have a di ei for one and dj ej for the other. So this di ei and dj ej appear as two separate interaction amplitude and whose product complex conjugate of each other constitutes a very similar looking transition probability expression which we have just obtained for the scalar field interaction. Similarly, when a spin of an atom talks to the background magnetic field, there also you would obtain a very similar looking expression for probability of transition across the atom, where the role of d will be taken over by the spin and the role of electric field will be taken over by the magnetic field. So you will have a SIBI and SJBJ kind of terms. And when I sum over all the possible states of the field, that means I do not care what happens to the field after all. I just care about what is the probability of the excitation from the ground state of the atom. I will end up getting expression of this kind, where you see the 2-point function of magnetic field this time, and its integral transforms dictates the transition probability across the atom. So despite we are doing academic exercise in some sense of discussing of monopole operator coupled with the field scalar field phi, all the realistic physically significant cases will be just replicable from this structure what we are talking about. So it's a good idea to keep pushing ahead with scalar field consideration, and more or less most of the ideas which we have discussed across this will be very similarly replicated across more realistic settings. So let us move forward and try to see what do we learn if I try to go ahead. So as you see, the 2-point function phi t and phi t primes, its expectation value across the vacuum state is required in order to undergo this integral transform. Now we know from our previous classes for scalar field, I can compute the 2-point functions across t and t prime through this integration. This is the mode functions representation of the 2-point function. This we have done previously in the class as well. So here e to the power minus I omega k t minus t prime plus k dot x minus x prime appears in the phase of the exponential, and then you have to integrate over all Fourier modes. Recall, in Fourier modes, harmonic oscillator structure is obtained for a scalar field. So effectively, we are summing over all the possible harmonic oscillator modes, which are identified with mode number k, and we are interested about t and t prime location in space, their separation, t minus t prime, and x minus x prime, the spatial separation. Now, here is an interesting assumption we have to make in order to do the computation forward, that in this exercise, the 2-point function is not only being computed at two different times, t upon t prime, we need to provide information at what locations, because field is a function of not only time, but different locations, field's values are different. So here, we have to use the spatial locations as the locations of an atom. So we are interested about not fields correlator across two arbitrarily separated spatial points, but only those spatial points where the atoms are at two different times, t and t prime. So how do I compute the locations of the atom? At this stage, we make an unsert of something called a semi-classical analysis for atoms. So atoms has let us say monoelectron atoms like hydrogen have 2 degrees of freedom. One is for the electron and one for its nucleus. Nucleus are typically multifold heavier than the electrons, and we presume that analysis of nucleus would be done classically. They are so massive that we need not consider their quantum properties for up to this accuracy where we are interested about. So heavy nucleus therefore would be assumed moving classically, and it is their locations where the field correlators will be obtained. And the electron around the nucleus is to be treated quantum mechanically, and therefore the operators of positions of electrons we are not putting it over here. The positions over here what we are putting are for the atoms. So atoms trajectories location are being used for x and x prime, and ultimately at these locations the field values correlations we are trying to get. Those correlations ultimately go under the integral transform and tell us what is the transition probability. For instance, let us think of an atom which is at rest with respect to us in the lab frame. So that means our lab frame becomes atom's rest frame as well. In that case, the spatial displacement would be 0 across two different times for atoms. So x would be the same as x prime for a future time as well as for the past time. So I would have a x minus x prime is equal to 0, which will take off the second argument in the exponent of exponential. So the 2-point function will just become the integral over e to the power minus I omega k t minus t prime. And that will go and sit in the 2-point function representation which we needed in order to get the transition probability. Now what we can do from here, we can flip the orders of integration. There are 3 integrations which are involved. 2 integrations in t and t prime and 1 integration in d3k. Actually, in that sense, there are 6 integrals, but I'm collectively calling 5 integrals, rather d3, 3 integrals in k and 2 integrals in t and t prime, but I'm collectively calling d3k as 1 integral. So what I do, I take the d3k integral at the last, and I separate out the 2 integrals in t and t prime. That means I will collect all the t dependency at one place, integrate it with respect to dt. I will collect all the t prime dependency at another place and do the integration with respect to dt prime. T dependency comes through in the exponentials argument of the first exponential as well as in the second exponential over here. So I can collect these together. You will get overall exponential minus iota and then delta E upon h bar from the first exponential and omega k from the second exponential. So this becomes the integral of dt, that all t dependency comes over here. So that integration we need to do. Similarly, if I collect all the t prime dependency in the system and collect it at one place, I will get this dt prime integral, which is over here. Notice one fact, that the integral dt with this exponential and integral dt prime with this exponential, they are just complex conjugate of each other. So I need to just compute one of the integrals, do its mod square, and then perform the d3k integral, and I will be done with getting to know the transition probability. Okay, so that's what we move ahead to, and let us compute the two integrals or the one integrals and its mod square, and find out what is the transition probability for an inertial atom, let us say, which is at rest. For those atoms, we can compute things, the probability of transitions, if the interaction is happening for a time duration up to capital T. So let us look at the transition probability between time small t varying from small 0 to capital T. So that means the two integrals which are appearing over here, they all are running from time 0 to capital T. So let's just go ahead and perform these two integrals and try to see what results do we get. I have a simple exponential as the integrand, which is a fairly simple exercise to do. You can see that you will directly get the exponential back divided by minus iota delta e upon h bar plus omega k. So that would be just the integral. When I put the two limits, for the upper limit I will get this term over here, and for the lower limit I will get a minus 1 just. Okay, small t would be put to value 0, and the denominator is common for both the terms. So now you can see I have a structure that I have an exponential of something minus 1 divided by minus iota. This thing together can be written in terms of some sine function. How do I do that? I pulled out e to the power minus iota, the same thing, capital T by 2. So this, if I pull out, I will be left with e to the power minus iota, the same thing over here, delta t by 2, minus e to the power plus iota delta e by h bar plus omega k t by 2. So whatever I have pulled out as a factor will be, its opposite will be put at the second place to reproduce the 1. And downstairs I have a minus iota, and you can see that according to that analysis I will get twice of sine delta e upon h bar plus omega k times t by 2. So what this pulling out of this exponential with half the phase factor gives me a sine in the numerator, and the denominator's minus iota goes into the definition of a sine. So all I am left with in the denominator is delta e upon h bar plus omega k. Okay, so therefore this is the integral which I would get for inertially non-moving atom in lab frame. The first integral will give me just this exponential, phase factor, and sine, as we just saw. Okay, now I have to take this and mod square this. The second integral is just complex conjugate of that. So if I do just the mod square, this overall extra phase will just vanish, and I will get a mod square of the whole thing. That means twice sine delta e plus omega k t by 2 divided by this mod square of this, which is our real numbers, so squares of individually that. What I do, I take this 2 and bring it down to the denominator. So overall I have this thing delta e plus omega k, delta e upon h bar plus omega k divided by whole 2. This 2 can be supplied downstairs. So when I do mod square, I will get a sine square in the top and the denominator by 2 whole square in the bottom. So I would have this as the whole probability of transition expression. Okay, because I have to perform the d3k integral still. However, I have this function which was the mod square of the two time integrals, dt and dt prime. Together, both of them gave me the sine upon this factor common with exactly cancelling phases. So I am left with this integral, last integral to perform. So this is a final answer for any arbitrary time capital T. Now suppose we take a time scale which is much larger than any of the time scales of the atom. The time scale of the atom is delta E upon h bar. Delta E is a typical energy gap in atom, divided by h bar will be the typical photon frequency which would be needed. But suppose I am looking at time scales which are much larger than 1 over this frequency. That means I'm waiting too long compared to the internal time scales. Internal time scales are 1 over energy gap upon h bar. That is the 1 over inverse of this frequency is the internal time scale of atom. So if my time is much larger than that time scales, I can approximate this expression to its infinite value limit. So I take this expression sine square upon this and take capital T tending to infinite limit of that in anticipation of a very long time value of probability. At late time, what happens to the probability? Again, if you have seen it before, you would know that the expression which is sine times something times x divided by the, call it the whole thing as a, delta E upon h bar plus omega k by 2 divided by delta E by h bar plus omega k by 2 and factor t is there. So it has a structure sine a t upon a and then t tending to infinity. That gives you pi times the delta function of a. So therefore, our a was this object delta E plus h bar plus omega delta d by h bar plus omega by 2. That will go and sit in the argument of delta function. So I will get the limiting value of this sine square integral would be just mod square or just a square of this pi times a delta function. So pi squared times delta square, two delta functions I will get with the same arguments. However, look at the expression which is inside the argument of the delta function. Delta E upon h bar, which is the transition gap of the atom. Omega k came from the field mode. Remember when we were writing down the 2-point function, the omega k appeared here for the first time. And this omega k was running. It will take different values corresponding to different k's. So therefore, this omega k is a continuously running value, but it is positive. Omega k is root under k square plus m square, if you remember. For massless field, it is just omega is equal to kc actually, but omega is in c is equal to 1 unit, omega is equal to k. That means this is also a positive quantity. So both delta E upon h bar and omega k are positive quantity. That means for any value of omega k in this integral, the argument of a delta function is always going to be positive, and argument of a positive argument of a delta function kills the function. So delta of any positive argument is 0. That means the ground state, sorry, this is oppositely written, it should be G2E. So ground state to excited state transition probability, somehow I have written it the opposite way. There was a typo over here, which I would correct in the notes. So the excitation probability is 0 if I wait for long enough time. So that means the inertial atom at rest does not get excited on its own. Okay, so this should be G2E. So that would become 0. So ground to excited state transition would not happen automatically if the field was initially in the vacuum. Here we have assumed the 2-point function is being computed in the vacuum state of the field. So if field has no photon to begin with, there is no likelihood in long time that the atom will automatically become excited. That probability turns out to be 0. Okay, in order to excite the atom, the field should initiate the discussion. The initial state of the field should be non-vacuum. In vacuum state, there is no probability of atom getting excited. On the other hand, if the field's initial state was non-vacuous, for instance, suppose initial state of the field was single photon in momentum k naught. So my in state would be replaced by the initial 1k naught. So recall the previous step where we had computed the probability. We had done this thing that initially the state was ground for the atom and vacuum for the field. This time it will become 1k naught for the field. So this will become 1k naught over here for the field part. And then if I compute the probability of atom going to excited and field going to any of the possible states psi, the probability of such a process will be obtainable from the amplitude of the transition, which will this time have a phi squeezed between 1k naught and psi. This is the same computation which we did for vacuum. You can go back to the previous class and check. Only thing happening here differently is this: previously the left hand side was vacuum, now it has become 1k naught because we are starting with a non-vacuum state. Similarly over here, the outermost state is again 1k naught instead of vacuum. So previously psi was the field phi was squeezed between 0 and psi, and this side it was psi and 0, and the summation over all Fock basis element created an identity here, and therefore the 2-point function of the field in the vacuum state was obtained. This time the 2-point function of the field in the 1k naught excited state of the field would be obtained. So therefore, if I try to ask for the probability of a transition for the atom from ground to excited, had the field initially been in the excited state 1k naught, that probability will be just 2-point function this time computed in 1k naught state and the same integral transform which we did previously. So that means we need to evaluate for this time what is the 2-point function's expression in 1k naught state. Recall previously we had obtained the 2-point functions in the vacuum state and obtained that as a simple integral of a d3k upon 2 omega k and exponential phase. This time also very similar kind of expressions will come about, but we have to correct for that the state is not vacuum. So let us write down the state which is 1k naught. The state 1k naught can be written as ak naught dagger acting on vacuum. So ak naught dagger acting on the vacuum will become my state. Similarly, its conjugate or the dual bra representation will be the bra 0 acted upon by ak naught. So this is just the Hermitian conjugate. This is just the bra 0, and this is just this is left hand side is the bra 1k naught, and right hand side is the kit 1k naught. In between there are two field operators at location t and location t prime, position x and position x prime. So therefore I write down the fields as this at location tx, and the second integral is just giving me the field expression at location t prime x prime. Now again you collect all the operators. All the operators are ak naught here, ak1 here, ak1 dagger here, ak2 here, ak2 dagger here. Recall, when I am writing the two fields as integrals, I am going to keep the labels of the integrals different so that I can differentiate between the field at location tx and field at location t prime x prime. So the first field, which is for phi, I am calling its Fourier decomposition as d3k1, and the second field phi t prime, its Fourier decomposition is being called as d3k2, and the labels of exponentials are accordingly adjusted. So all these exponential, all these integrals are just real quantities or complex quantities, but not operators. So I can take all these things out of the operator action. Only states or operators will act on each other. So I will collect all the operators between the states. So all the state which we are looking at is the bra 0 on the extreme left and kit 0 on the extreme right, and there are operators in between. So let us start collecting the operators which will survive. This operator ak2 dagger, and I have a ak0 dagger here, and similarly left hand side I have a ak naught operator hitting on the bra 0, and then I have a two operators ak1 ak2 ak1 dagger here. Now we know from our previous exercises such an expression will survive if I have the same state from left and right. They survive under operations only if we have same number of AK and AK dagger hitting each other. So that means I can have one AK knot is from the left and one AK knot dagger from the right are already in the game. So that means I have only luxury of arranging one AK and one AK dagger from these two operators. The two fields operator can only supply me one AK and one AK dagger from each, such that I can write a surviving operator structure. One possible surviving term will be when this AK knot and this AK1 are one hand together, while this AK0 dagger and this AK2 dagger are on the other hand together. So this will be the first term which will be contributing. Their phases have to be adjusted. Adjusted meaning written in the way they appear. So I have a e to the power I k1 dot x from the first term and e to the power minus I k2 dot x prime from the second term, which I have collected and put aside. Similarly, one more set of operator which will be surviving will be AK naught combining with AK1 dagger, then AK2 and that combining with AK naught dagger here. So AK naught, AK1 dagger, AK2, AK naught dagger. And their exponentials again will be e to the power minus iota k1 dot x from the first AK1 dagger and e to the power plus iota k2 dot x prime from the second term. So collectively, the second term is this. Now you can verify all other terms which will appear in this expression will vanish. For example, AK0, AK1, AK2 and then AK0 dagger, its expectation across vacuum state is 0. Similarly, AK0, AK1 dagger, AK2 dagger, AK0 dagger, its expectation value across vacuum is 0. So only two terms will be surviving this exercise. One is AK0, AK1, AK2 dagger, AK0 dagger. So that's what we have to compute. And another term is AK0, AK1 dagger, AK2, AK0 dagger, which is whose expectation across vacuum. So let us go ahead and compute these two operators. The first one is AK0, AK1, AK2 dagger, AK0 dagger. In between, I see AK1, AK2 dagger has appeared. That I'm going to write as their commutator. I already know AK1, AK2 dagger commutator is delta K1 minus K2. That means AK1, AK2 dagger will be delta K1 minus K2 plus AK2 dagger AK1. So the commutator is delta K1 minus K2. The commutator has two terms, AK1, AK2 dagger minus AK2 dagger AK1. That minus AK2 dagger AK1, I bring it on the right hand side of the commutator. Therefore, the AK1, AK2 dagger becomes this. Okay. And as before, AK0 and AK0 dagger are appearing on the left and the right respectively. So then I open it up, the square bracket, I open it up. I will get two terms. First term is delta K1 minus K2, which is coming with identity, which is, I'm not writing over here, but there is an identity multiplying delta K1 minus K2. But ultimately, that delta K1 minus K2 will come out and only AK0 identity, AK0 dagger will survive inside, which is equivalent to AK0, AK0 dagger squeezed between the vacuum. That will be the first term. The second term will be AK0, AK2 dagger, AK1 AK1, AK2, AK0 dagger squeezed between the vacuum. This AK0 dagger and this AK0 and this AK0 dagger squeezing the AK2 dagger and AK1 in between. Okay. Again, I have a structure where I have a AK0 and AK2 dagger coming along and AK1 dagger, AK2 dagger coming along. These two can also be written in terms of their respective commutators. The first pair which is appearing over here can be written as a delta K0 minus K2 plus AK2 dagger AK0. Use the commutator between AK0 and AK2 dagger to write the first square bracket here. Similarly, AK1, AK0 dagger can be written as the second square bracket over here. And now you can see I will have many terms coming about. First term is just delta 0. The first term which I'm going to write over there here is delta K1 minus K2, which is coming from here. And then AK0, AK0 dagger. if I try to compute, you can see that this in this object is 1k not 1k inner product, which will just give me delta 0. Remember, 1k not state has a normalization of a delta 0. So this squeezing is going to give me a delta 0, and I will have a delta k1 minus k2 multiplying it. Now in this square bracket, I have many terms. This delta k0 minus k2 can multiply this delta k1 minus k0, and then the vacuum squeezed. Vacuum is normalized, so I will get first term as delta k0 minus k2 times delta k1 minus k0, and the normalization of vacuum state, which is 1. All other terms you can see are going to be 0, because on all other terms, one AK operator is going to hit upon 0. So this operator hitting the 0 will be 0. Similarly, this AK not hitting the 0 will be 0, or AK2 dagger hitting this 0 will be 0. So you can verify, apart from the two delta functions multiplying each other, all the other three terms which get generated in the cross multiplications, their expectations are 0. So that means the first term which has appeared over here is just products of delta functions in funny way. The first term is delta 0, delta k1 minus k2. The second term is delta k0 minus k2 and delta k1 minus k0. So this is true. This is for this whole term. Now I know the whole term because I have completely computed the first expectation value. You can see the second expectation value is not much different. We have indeed computed something very similar already. We have computed the expectation value of this operator which appeared in between, which has a very similar structure like what we wanted to compute for the second term. So so therefore we can write down that AK0 AK1 dagger and AK2 AK0 dagger would be the same as almost the expectation of this term, which appropriate identification what was k1, what was k2, and what was k0. And you can see that even this term's expectation value is just a product of delta functions. Okay, so ultimately all the first term is sum of two products of delta function. The second term is just one product of delta function. You can verify this by playing around with the commutation rules. So therefore, the correlator of interest, the 2-point correlator of interest between 1k0 and k0 just becomes integral transforms over various delta functions multiplying each other, and then the exponential phase. So the first set of operators which was getting squeezed between the vacuum state was this AK0, AK1, AK2 dagger and AK0 dagger with exponential phase k1x minus k2x prime. So therefore, these two delta functions which are appearing over here, they overall will get multiplied with the same exponential phase, which is the first term. While the second set of delta function product will just get multiplied with the complex conjugate of the first one. So that's what happens. I just write down the two terms separately of the delta functions, meaning I will have a delta 0, delta k1 minus k2 coming with this exponential phase, delta k0 minus k2 times delta k1 minus k0 with the same exponential phase like first term, while the second term delta k0 minus k1, delta k2 minus k0 comes with a complex conjugate of the exponential phase. Now since I have the integrations under control for the at least the 2-point correlator, I will do away with all the d3k integrals. So when I do the d3k2 integral, this delta function here will set that all the k2s in this term should be replaced by k1. When I do the k2 integral in this term, it will just set me that all the k2 integrals, all the k2 values should be put to value k0. And similarly in the last term, I do all the k2s should be put to value k0 under the integration. So the d3k2 integrals can successfully be done using all the delta functions. I will get the first term will become e to the power iota, k1 now will become common thing. It will be dotted with x minus x prime and the delta 0. So this integral will contribute that. The second integral k2 will be put to value k naught. So in the exponential and in the exponential k2 will take the value k naught. But you see even the k1 integral has the similar thing, that k1 integral will be put to value k naught as well. So both the integrations can be done in this middle term, and it will just put all the k1 and k2 to value k naught. Okay, so therefore the second term I will get is e to the power minus iota k naught dot x minus x prime divided by twice of k naught. Root 2 omega k coming from will become 2 omega k root under 2 omega k naught from the k2 integral, and similarly t3 k1 integral will also convert square root of 2 omega k as root square root of 2 omega k naught. Together they become 2 omega k naught. Similarly, you can just do the last integral. Also, you will see that you will still get 1 over 2 omega k naught from these things. Only thing changing with this exponential phase will become the same thing, but the complex conjugate of each other. So you see, once I have taken care of the k2 integral in the first term, and while both k1 and k2 in the second and the third term over here, I get this structure. So let us go ahead and see what are we up to under this. In the transition probability expression, what we needed to compute was the double integral in dt prime with this exponential weightage of the 2-point function. Now, since I have taken the initial state to be 1k naught and not ground state or the vacuum state of the field, that state 1k naught we know is not normalizable. That means it is not automatically normalized. 1k naught inner product is not 1. So it is good idea to define things in terms of normalized state. That means I divide the whole expression by normalization of the state 1k naught. So I take this, divide by the expression of the probability, divide it by 1k naught, that will be normalized probability. When I do that, normalization of 1k naught is just delta 0. So 1 over delta 0 extra factor I have to compute. I have to put in getting a normalized probability in the whole expression. The whole expression before was just this and the square box put together. That was the 2-point function, and the double integral in the times that tells me what would be the total transition probability. But since the state was not normalized, I should divide this thing with the normalization of the state. So I get this 1 over delta 0 extra factor. Now spot one thing. This delta 0 is here. For a moment, just forget it. Then look at the exponential thing which is multiplying that. This is exactly the 2-point structure which we just dealt with. Remember, when we were dealing with initial state being the initial state being the vacuum, the 2-point function was just this integral d3k omega k t minus t prime plus k dot x minus x prime. Together it is just e to the power iota k dot x minus x prime. So the same thing has appeared multiplying delta 0 this time. Okay, so this is the 2-point function of the vacuum. This gets multiplied with delta 0 because this integral itself was coming with the delta 0. But fortunately, since we are looking about the normalized probability distribution, normalized probability of transition, 1 over delta 0 also gets multiplied. So these delta 0 and that delta 0 exactly cancel each other. And I am left with the first term, which is just the vacuum transition probability. Okay, which we know for long time average was 0. So therefore the horrendous term, which was a delta 0 kind of thing, which was somewhat problematic, does not contribute anything to the probability transition. But still there are 2 more terms which are left. These are the terms which we'll try to see if there can be a transition or not. Again, for inertial atoms, I will open up this dot product. K naught dot x minus x prime will be omega k naught times t minus t prime minus plus iota k naught dot x minus x prime. Again, for inertial atom at rest, this portion will be just washed out. There x minus x prime is 0, and only the temporal integral would be the temporal part of the exponential will be surviving. That should go and sit in the 2 places, here and here, two terms appearing over here, they have to undergo the integrals, and they individually become e to the power minus iota omega k naught t minus t prime, and the second one will become e to the power plus iota omega k t minus t prime. And outside there is a exponential minus iota delta e upon h bar t minus t prime. So you can just write these two terms, combine these exponentials, you will get the first exponential is e to the power minus iota delta e upon h bar plus omega k naught coming from the first term, and the second thing will be just e to the power minus iota delta e upon h bar t minus t prime minus omega k naught this time from the complex conjugate term, which is the second term, which is over here. These integrals we have already evaluated in the vacuum exercise as well, vacuum 2-point correlator exercise as well. And we know the first term is again going to give me pi times delta of e upon h bar plus omega k naught by 2 whole square. This integrals we have computed before. And the second term will similarly give me delta of delta e upon h bar minus omega k naught this time. Because of this complex conjugate term comes with a negative sign, the two exponential combine each other with a relative negative sign in between. So I will get a delta function of delta e upon h bar minus omega k naught divided by 2 this time in long time average. So this integrals we had computed before, and just using this argument once more and writing these two terms like that. So now this first term, which has delta function with a positive argument, anyway this is going to become 0, so this will not contribute in the transition probability. But the second term might. The second term will survive because there is a probability that omega k naught and delta e upon h bar of the same value, then this term will become non-zero. Even if omega k naught and delta e upon h bar are magnitude wise same, the first delta function does not survive. The second one survive only when the photon frequency k naught was the state which was vacuum, which is replacing the vacuum of the field. If the photon frequency is the same as the energy gap, then the transition might happen. The statement is that the probability will become non-zero only if the delta function is saturated. That means the photon's frequency is the same as the energy gap. If you excite the atom, if you excite the field, the initial state is 1k naught, where 1k naught is very different from delta E upon h bar, then even the second delta function will become 0. That means this probability only survives when the initial state has the same energy as that of the energy gap of the atom. And what is the probability? Again, there was a normalization division. The square of a delta function can be written as the first delta function times second argument becoming 0. Delta x whole square can be written as a delta x times delta 0. So that's what the trick I have used. And division by delta 0 coming from the norm of 1k naught states, they cancel each other. So delta 0 cancel each other. And then the survival probability is this. The probability of transition is just the part which is remaining, just the part which survives is this. This has given a wrong sign, wrong box formation. So okay, so this is the expression which will survive. This tells only transition which is allowed through interaction of the field with the atom is if the field has one photon in itself which has the same energy as that of energy gap of the atom, then only the transition will happen, otherwise it will not. Okay, this is very much reasonably expected. So Unruh-David detector root at least is telling us the results are consistent with our expectation. If there is no photon in the field, the atom should not get excited. If there is a photon in the field, the atom may get excited depending upon the photon in the field has the same energy as that of atom's transition lines or not. So that is very well reasonable approach. So therefore the learning is that resonance condition, this is called the resonance condition, that the photon and the energy gap of the atom are the same. However, we have computed this thing for long time average, t tending to infinity. Okay. However, in long time average, we cannot just rely on the leading order perturbation theory. Remember, when we started doing the business, the time ordered exponential, we had truncated the higher order contribution, saying that the leading order contribution is the dominant one. But you can check for yourself that higher order terms which we had thrown away, they are small at small time steps. If I wait for large and large and large time, they will not remain small enough. So they will become, they have a tendency to grow for longer times. That means if I literally take t tending to infinity, I have to account for all order terms of the time ordered exponential, not just the leading order. So therefore, this result which we have obtained, the photons cannot get excited if it is in vacuum, or photons get excited if their frequency, if atoms get excited if the frequency of the photon in the field is same as its energy gap. All these results cannot be fully trusted. Or one can reverse the game and say that t tending to infinity, by that I really do not mean infinity, I just mean t is much greater than the internal time scale which we just discussed in today's set of today's discussion, that t much greater than delta h bar upon delta e is as good as t tending to infinity. So I do not really mean t tending to infinity, I just mean t much greater than the internal time scale. But this time scale should be smaller than the time scale at which the second or higher order terms in the perturbation theory start becoming important. So remember what we had thrown out in the time ordered exponential. If when we were doing the interaction picture, we had retained only the leading order term, which was this integral. We had thrown out the second order term, which was this term. When these two terms become starting to compete against each other, that means when they become of the same order, from that point onwards, I cannot do perturbation theory up to leading order. That means perturbation theory breaks down over there. So therefore, there should be the upper limit of integral T naught, after which leading order perturbation theory is not good enough. So if I take my evaluation probability of transition time, capital T, much larger than the internal time scale of the atom, which is h bar upon delta E, but much shorter than the time scale at which perturbation theory breaks down, then whatever we have computed is good enough. Only thing you have to keep in mind, the delta functions and other things which are really true for t tending to infinity, they will not appear, but their cousins will appear. That means t for very big functions, for very big value of t, but smaller than a particular number which is t naught, which is really very high. So t much greater than h upon delta e, I will get very close to a delta function. Not exact the delta functions which we are getting here, but some function which is very good approximation to a delta function. So therefore, in this time scale, where I am much larger than the internal time scale of the atom, but much smaller than the time scale at which perturbation theory breaks down, till that time scale our analysis is trustworthy enough. It is not exactly correct, but trustworthy enough. So whatever we have obtained, that the photons will not able to excite, the vacuum will not be able to excite the atom, will definitely will not be able to excite the atom, at least for a long time period, capital T, which is larger than its internal time but shorter than the perturbation theory's limit. And similarly, single photon, if it is present in the field, will excite the atom if its frequency matches with that of the energy gap required. That is trustworthy enough for a sufficiently large time period. Okay, fine. So then we stop over here, and these are the natural generalizations which we see, which are intuitively correct. Only thing of interest is that our intuition runs within this time window, larger than h over delta E and shorter than t naught. After that, the perturbation theory breaks down, so our expectations may or may not fructify. Smaller than this time period, our integrations are not under control. They are not giving us delta function. So shorter time scales we do not know. Really longer time scales we do not have the perturbation theory at our hand. So therefore, but there is a window where we can apply the perturbation theory, which is big enough for us. So whatever we have discussed is not wrong. It just operates in a longer time period, but not really infinity. Okay, so we stop over here. In the next class, in the next week's discussion, we will start seeing the counterintuitive results. What happens if the initial state of atom was excited? Is there any probability that it will go down on its own or in presence of a atom in the field? Those are the discussions regarding to something called spontaneous emission and stimulated emission that we will see in the next lecture. Okay, so we stop here.